Hello everyone and welcome to FPGA, Verilog and Vivado tutorials. In this tutorial we explain how to control a 7-segment display in FPGAs. We are going to implement a binary to decimal converter and display decimal numbers. For example, over here you can see one of the 7-segment displays. We are going to control this display by using these 4 switches over here. For example, if all the switches are off, then the number is 0. And this is consistent with the binary number notation shown over here. On the left hand side of this equation, you can see a binary number, and on the right hand side, you can see the corresponding decimal number. So, if we turn on the first switch, you will see that the number 1 is displayed. This is consistent with this equation. Consequently, to produce 2, we will turn off the first switch and turn on the second switch. Consequently, we have this equation over here. And we proceed further. For example, to produce 3, the first and the second switch should be on. Similarly, to get 4, we need to turn on the third switch, and etc. For example, to produce 9, we need to turn on the fourth and first switch. Finally, if we, for example, go above 9, that is, if we turn on first and the second switch and keep the fourth switch on, the error will be produced. Okay, let's start with explanations and with Verilog implementation. In this tutorial, we are using Nexys A7 100T FPGA. This is a very popular FPGA that is often used in electrical and computer engineering programs in the US and Europe. However, everything explained in this tutorial can easily be used in the case of other FPGAs. This FPGA has 8 7-segment displays. They're located over here, and you can see all 8 of them. 1, 2, 3, 4, 5, 6, 7, and 8. Currently, only the first display is active. Every display has 7 segments. We will use the first 4 switches to control the 7-segment displays and to display the numbers from 0 to 9. The switches are located over here. This is the switch number 1, this is the switch number 2, then the switch number 3, and the switch number 4. We will convert 4-bit binary numbers that are entered by using switches to decimal numbers that are displayed on the 7-segment display. For example, if we enter first switch off, second on, third off, and fourth off, this produces the binary number 0010, and consequently, number 2 is displayed. A single 7-segment display has 7 LEDs. These LEDs are also referred to as cathodes. The LEDs are shown over here. We control the LEDs by sending 7-bit binary numbers. The LEDs are denoted by A, B, C, D, E, F, and G. We can group them in a single 7-bit binary number, A, B, C, D, E, F, G. To turn on a particular LED, we need to send a 0 bit. Consequently, to display the decimal number 2, we need to send A should be 0, B should be 0. This will turn on both A and B LEDs. Then C is 1. This will keep the C LED off. Then D should be 0, that is, we want to turn on D. Then E should be 0, we are also turning on E. Then F should be 1, that is, F should stay off. And finally, G should be 0. This will display the number 2. To do that, we need to send 001, 0010. In total, there are 8 displays. We control which display we are going to use by selecting a particular anode. That is, we need to send an 8-bit binary number where every position encodes a particular display we are going to use. For example, if we plan to use the first display from the right, that is this display, we need to activate anode 0. Or, better to say, we need to send 0-bit to anode 0. The corresponding binary number will be 1, 1, 1, 1, 1, 1, 1, and 0. This will turn off all first 1, 2, 3, 4, 5, 6, 7 displays, and it's going to only keep on the last displayed over here. The Verilog implementation is relatively simple. Over here you can see a piece of code that will convert a binary number to a 7-segment display binary code. We start with an always statement where the sensitivity list of the always statement consists of a number. A number is a 4-bit wide binary number, and this number is actually entered by the user. It can take a number of values, and over here we are going to write a case statement where we are going to do a particular assignment for a particular case. For example, if the provided binary number is 0000, 7-segment display code will be 7-bit wide, then we will have first 6 zeros and 1. What will happen over here? This will actually turn on all the outer LEDs, and it will turn off this middle LED, and in this way we will produce 0. And then if a user provides 0001, this means that 1 needs to be displayed. Consequently, only B and C LEDs should be turned on, and consequently the code is given over here. Keep in mind that 0 means that a particular LED will be turned on. And over here you can see the order of the LEDs. Consequently, if you, for example, see this binary number over here, you know that A is turned on, B is turned off, then C is on, D is on, E is off, and F and G are on. And consequently, the produced or displayed number will be equal to, let's see over here, this number is 4 plus 1, this is number 5. And that's the basic principle. Okay, let's start with implementation. The first step is to find your board schematics. Consequently, open your favorite search engine and search the name of your board and add schematics. In my case, the board schematics is given on this official Xilinx website. I will post a link to this website in the description below this video. If I scroll all the way down, in this feature document section, I can find my schematics in the reference manual. So let's click over here, and this document will open. Now, if I move all the way down, and if I go to the page 18, I will find this very important diagram. This diagram tells me how switches and LEDs, as well as the anodes, are connected to the FPGA. And these numbers over here are very important. These are the pins, and they need to be used in our Verilog and Vivado implementation. The next step is to create a Vivado project. For that purpose, click on Start and search for Vivado. As you can see over here, I'm using Vivado 2024.1. However, you can also use a newer or an older version of Vivado. The implementation process will be the same. So let's start Vivado. Then let's wait for a while. And let's click on Create Project, then click on Next, click on Next, click on Next, and let's select our board. Click on Boards and search your board. In my case, the board is Nexys A7 100T. Click on Next and click on Finish. Okay, here we are. The first step is to create a constraint file. The constraint file will connect the physical switches, LEDs, and anodes with the pins of the FPGAs that are shown over here. So let's do that. Click over here, click on Constraints, then click on plus, make sure that Add or Create Constraints is selected, click on Next, click on Create File, and let's call the file Constraint. Click OK, and click on Finish. And then, after some time, over here you will see the constraint file. Double-click on the file, and let's start editing this file. I will expand this window, and to make this video tutorial as short as possible, I will simply paste the content of this file, and I will explain it line by line. Okay, so let's start with these 4 statements over here. These 4 statements are connecting switch 0, switch 1, switch 2, and switch 3 with the pins J15, L16, M13, and R15. So let's see how it's done. We need to type set property dict, standing for dictionary. Then over here, inside of braces, we need to write package pin. Then we need to specify the first pin name. Going back to the schematics, we can see that switch 0 has to be connected to the pin J15. So over here we specify J15, which is the name of this pin. Then we use IO standard and we type LVC MOS33. Then over here in the square brackets we type get ports. Then we type switch 0. Note over here that this port is written inside of braces. We close the square brackets and we add the semicolon. Also notice over here that we have space after dictionary and space after these braces. So what's happening over here? Over here we are connecting port switch 0 to J15. Note that I introduce name over here switch, and note in the subsequent statements that we have switch 1, switch 2, and switch 3. In fact, switch is a port whose width is 4 bits. And in this way, we are accessing the particular bits. That is, I'm saying to Verilog and to Vivado that these switches over here and their on and off actions will be stored inside of the port switch 0, switch 1, switch 2, and switch 3. Consequently, if a user presses switch 0, this means that on this port switch 0 over here, I will see 1. Otherwise, if switch 0 is open, on this port over here, I will see 0. And the same thing applies to switch 1, switch 2, and switch 3. This is how we connect ports with the pins. This port over here, switch 0, 1, 2, and 3, will be used in a Verilog module that I will define later on. Next, we need to connect our cathodes. How do we do that? Well, we use the same principle. We say set property dictionary, package pin is the same, IO standard is the same, and this thing is the same. Now over here, we need to find a pin number. So let's do that. Let's look at the schematics and let's start with A cathode. Here it is. Okay, this cathode is connected to T10. Now, over here in my constraint file, I'm using a port whose name is segment, and I'm saying that the bit corresponding to cathode A will be stored in segment 6. This is what I'm doing, nothing more, nothing less. Then I'm doing the same thing for the other 6 cathodes, since if you remember at the beginning of this tutorial, we mentioned that we have in total 7 cathodes. Consequently, B is connected to R10. Over here I have R10, and over here I have segment 5. Consequently, the bit corresponding to this cathode over here will be stored in segment 5. In fact, segment is a 7-bit wide port, and this port is used to control the cathodes and to display numbers. Let's continue. Cathode C is connected to the pin K16, and consequently over here I have K16 and segment 4. Next, we can see the D cathode is connected to the pin K13. Consequently over here I have K13, and over here I have segment 3. Let's continue. Then E cathode is connected to P15. Consequently over here I have P15 and segment 2. Then cathode F is connected to T11. Over here it's written T11, and over here segment 1. And finally, cathode G is connected to L18, and over here I have L18 and segment 0, and that's it. Next, we need to do the same thing for the anodes. Here's how we do it. First of all, we have a port that is 8-bit wide, and every bit of this port will be used to control the corresponding anode. The anodes will be used to control which display will display the number. In our case, it's going to be the rightmost display. So let's look into the schematics. Here it is. And let's start. We have that AN, or the anode 7, is connected to U13, and consequently over here we have U13 and anode 7. Then let's continue. Over here we have K2 AN 6, consequently we have K2 anode 6. Then we have that anode 5 is connected to T14, and we can confirm it over here. Anode 5 is T14, then anode 4 is P14, P14 anode 4. Anode 3 is J14. Let's continue that and confirm. Here it is, J14. Then we have that the anode 2 is connected to T9, anode 2, then we have T9, then we have anode 1 is connected to J18, anode 1 J18, and finally anode 0 is connected to J17, and consequently over here we have that anode 0 is connected to J17, and that's it. This is our constraint file. Let's continue. The next step is to create our main module. This module will decode binary numbers that are set by the user, and it's going to display the corresponding decimal number. So let's create that module. Over here, click on Design Sources, then do the right click and click on Add Sources. Make sure that Add or Create Design Sources is selected, click on Next, and click on Create File. Let's call this file simply as decoder. And let's click on OK, click on Finish, and click on OK. And click on Yes. And after some time, click over here, double click on the file, and let's start editing this file. Here, to save time, I will simply copy and paste the content of this module. And let's explain this module line by line. First of all, this first line really doesn't matter in this particular simulation since we are not using a clock, so you can simply ignore it. Over here, we say module, and the name of the module is decoder. This module has two ports. The first input port is 4-bit wide, and it represents the number. This is the number that's entered by the user by pressing on or off the switches. For example, if the user presses the first, second, third, and fourth switch, then this input will be 111, where 1 represents if the switch is on and 0 represents if the switch is off. In this way, we can encode the type of the user input. Good. Then this module has an output. This is an output port. We declare it as a reg. Since this output port should continuously send bits, that is, it should not be a wire, it should store a variable and send this variable, that's why we have reg. It's a 7-bit wide and its name is 7 segment. Basically, this is the output of this module. And this output will be used to control the number that will be displayed on our display. Then, over here we have this always statement. What is the purpose of this always statement? This always statement executes this block that starts at the line 6 and ends at the line 30. Namely, inside of the parentheses we have the sensitivity list of always statement. Whenever any of the bits of our number change, this block over here will be executed. And that's the main principle. That is, whenever user presses on or off our switch, this block over here will be executed. And inside we have a very familiar statement, which is a case statement. This statement is the same statement as the case or switch and case statement in Python, C, C++, or MATLAB. So what are the cases? If all 4 switches are off, then we should display 0. And this is how we do it. We turn off all the, or basically we turn on, this is very important, zeros means that we turn on, so let me repeat. We turn on all the cathodes except the last one. So let's see what's happening over here. If I go back to my schematics and if I scroll down, here's what's happening. Basically over here, I'm turning on A, B, C, D, E, F, and G over here is off. That situation is encoded by this 7-bit binary number, where again, 1 means off, LED is off, and 0 means on, and this is number 0. Then, here is number 1. If this number is 001, that is, if a user presses only the first switch, the number that should be displayed is 1, and this is how we control it. And let me explain this number so you can better understand what's happening. So over here, A is 0, B and C are on. So let's see. A is 0, B and C are on, and that's obviously 1. And let's see what's happening with the other variables, and everything else is off. And consequently over here you will see 1, and that's the basic principle. And we do the same thing for the other numbers, for the number 2, for the number 3 over here, then for the number 4 over here, for the number 5, for the number 6, for the number 7, for the number 8, for the number 9, and what's happening over here? We have a default version, namely, if a user, for example, presses all 4 switches on, we cannot display that number. Consequently, over here we are going to display error, or E. That is, this letter is letter E, and that's it. Let me show you again this file so you can nicely type it from line 1 to line 14, then from line 14 to line 26, and from the line 26 until the end. Okay, so this is our decoder module. And finally, we need to create our main module. So let's go back over here on Design Sources, do the right click, click on Add Sources, and click Add or Create Design Sources. Click on Next, click on Create File, and let's call the module as Main Module. And let's click on OK, click on Finish, and click on OK. And yes. So let's click on Main Module over here. Over here, to save time, I simply copy and pasted the content of this module. So let's explain what's happening over here. First of all, we have this input port, which is a 4-bit wide, and its name is switch. And now, pay attention. This name over here is precisely the name in our constraint file. That is, in this way, we connected our physical pins on our boards with our variable and port names. So again, switch should precisely be the name that is equivalent, or better to say, that's precisely equal to the name inside of our constraint file. And the same thing needs to be applied for segment and anode. That is, segment is a 7-bit wide output port, and if you go back to the constraint, you will also find segment. Then we do the same thing for the anode. Anode is an 8-bit output port, and over here in the constraint, here is how it's being connected to the physical pins of our board. This is very important. Now, the ports and the variable names are connected. That is, the pins on our board are connected to the port names and to the variable names. So what is the purpose of this module? First of all, over here, we will enable the first display. To enable the first display, we send ones to all the anodes except the first bit of the anode, that is to the first anode. And in this way, we will turn on the first display. If you want, for example, to turn several displays at the same time, for example, this one and the first one, the last one and the first one, then here you will specify 0. On the other hand, if you want to turn on this one, you will specify 0 and you will turn off this one. So let's go back to the original case. That is, this should be the configuration. And over here, we instantiate our decoder module. We say decoder, which is the name of our module that's used to decode. Then we call simply as test, and over here we connect the ports and variables. Namely, the port of our main module is connected to the port number of our decoder. And we do that by typing dot, then the name of the port inside of our decoder, and then over here in parentheses the name of the port in our main module. And we do the same thing for the 7th segment. That is, the 7th segment port or variable should be connected to the segment of our main module. And that's it. Now everything is connected, we can save everything, and we can proceed further. First of all, we need to run the synthesis. Find this option over here, click on Run Synthesis and click on OK. And be patient. This step might take even a minute or so. Over here you can see that something is working, and if you expand over here, you can see also here that a computer is computing. And then after some time you will see this window, and you can either click over here and click on OK to run implementation, or you can simply click on Cancel and click over here on Run Implementation. So let's click over here and click on OK to run the implementation, then click OK. Again, the implementation step will also take a while, so consequently be patient. Then after some time you will see this window. Click here on Cancel. Next, click here on Generate Bit Stream and click on OK. This will generate the bit stream, which is again one of the last steps before we can actually upload our program. Again, be patient, since this step might take a while. Meanwhile, you can plug in your board through a USB cable to your computer. You heard this sound. This means that now my board is connected to my computer. And finally, after some time, you will see this window, then click on Cancel. Then over here, find this option, Open Hardware Manager. So click over here. Then over here, click on Open Target. But however, before you do that, make sure that your board is connected to your computer through the USB cable. After you connect through the USB cable, click on Open Target and click on Auto Connect. This will auto connect your board to the computer. Okay, now expand this window over here and then click over here, do the right click and click on Program Device. And click on Program, and this will program the device, that is, the code will be uploaded to your board. And now you can perform testing. That is, go back at the beginning of this video tutorial and see how we perform testing. Okay, that's all for today. I hope that you like this video. If you like the videos I'm creating, please support this channel or press like and subscribe. Thank you and see you in the next video tutorial.